Hi everyone. Okay, so we are doing the second part, which is elastic and inelastic collisions. Okay, and here we go. So when we're looking at elastic and inelastic collisions, we are going to take a look at three different kinds of collision. Oops. And they are as follows. The first one is known as an elastic collision. Okay. And in this elastic collision, what you have is the EK of the two objects is conserved. So EK before equals to EK after. And the momentum, of course, of the two objects is conserved as well. So momentum before equals to momentum after. Now an example for this could be if I have two super balls colliding, and you're probably thinking, what is a super ball? Not a Super Bowl, okay? What is a super ball colliding? Okay, so by a super ball I mean, so if you think about tennis balls, okay, tennis balls got a fuzz on them, right, or around them. If I bounce a tennis ball over time, what happens to the tennis ball's bounce? It reduces, right? Because you know that some of the energy is being lost either to sound, to thermal energy, to particles just motion, and so on and so forth, correct? But a super ball would be, you know, those little the ones that you get from the dollar store where you bounce really high. Okay, that's a example of a super ball where the energy is not lost. We also call them bouncy balls. So imagine I have two bouncy balls and they are colliding with each other. Now if they're colliding with each other, what will happen is, of course, the energy of the system, none will get lost. None of the energy of the system will get lost, and none of the momentum will also get lost as well. Yes. Yes, they do lose energy in real life too. I mean, not as much as a tennis ball. Okay. I'm not sure. Has anybody ever played squash before? Do you know what squash is? Yeah. Yeah, pretty sick. I love squash too. So squash, if you ever played squash, when the ball is cold, it doesn't bounce at all. But once you warm it up by smacking lots of it, okay, like really smacking it hard, okay, I wanted to say something else. Okay, I don't know if you ever have a good game of squash and you smack it, that ball gets really warm and bounces a lot. So the temperature affects how it bounces. Okay, goodness gracious. Oh, everybody's laughing now. Okay, next one. So this is an inelastic collision. Okay, inelastic collision. In an inelastic collision, this would be an example of two, for example, tennis balls bouncing or colliding with each other. Two tennis balls colliding. Okay, and in this situation, your EK before does not equal to your EK after, but the momentum before equals to the momentum after. So we are going to do these questions for sure. Number one. We're not going to do number two that much. We're not going to do that one. Okay? And the third kind of collision is completely inelastic collision. Completely inelastic collision. So in a completely inelastic collision, an example would be two balls of Play-Doh or silly putty. Okay, if imagine two balls, I throw two balls of Play-Doh towards each other, what would happen to them after the collision? They would stick together, correct? And that's basically what happens here. So the two combine, they combine together. Okay, so this is a completely inelastic, meaning the EK before is less than the EK or greater than the EK after, but the momentum before does still equal to the momentum after. Yeah? Oh, don't worry, we'll talk about that. Momentum does not disappear. Okay, are we good with this? Yeah? Yeah, so when when an asteroid hits Earth, for example. The asteroid becomes part of Earth over time, right? Or actually right after the collision. So that would be an example of a inelastic collision. Okay? Or if you had a train and a Mini have an accident, completely inelastic. The Mini doesn't make much of a difference to the train. The train's so massive. Or the big rigs that you have, big trucks, they get into an accident with a motorcycle. I mean, not much that the motorcycle does to the big rig, but it becomes a completely inelastic collision because the two literally combine together after the collision. Does that make sense? Okay? All right. Okay. So what we're going to do is we're going to start out with the first one. Can I erase this? Yes. So we're going to start out with the first one. And in the first one, we are looking at, now I'm going to use the example from the new textbook for this one, but we have a similar example in the old textbook as well. So fear not. And the question is as follows. This is sample problem number 1, page 235 in the new text. Okay. And the question is as follows. It says, suppose you have two balls with different masses involved in a perfectly elastic collision. So it's an elastic collision, which means both kinetic energy and momentum are conserved before and after the collision. Okay, so ball 1 has a mass of 0.26 kilograms. Traveling at a velocity 1, which is 1.3 meters per second. It collides head-on with a stationary ball 2. So V2 is not moving, 0.0 meters per second. And mass 2 of the second ball is 0.15 kg. And the question is, determine the velocities of both the balls after the collision. So we're looking for V1 prime and V2 prime. So what we're going to do is we're going to start out first. By the way, this is going to take a long time to finish. So I'm not sure if I'm going to have enough time to finish it on the recording. But we'll continue anyway regardless. Okay? Okay, so momentum before equals to momentum after. So we're going to start out with m1 v1 plus m2 v2, which equals to m1 v1 prime plus m2 v2 prime. Now, the textbook, as well as the formula sheet, has shortened formulas for you. You are not allowed to use those shortened formulas. You have to prove to me right from the beginning for every single question. Does this make sense? I say this again. You have to do the way that I'm doing it for the whole question, for every question. You're not allowed to use the shortened formulas that are in the formula sheet or in the textbook. Okay, so my velocity is 0. So that object is not moving, stationary. Okay, so we're going to just add the thing in. So this becomes m1 v1. Bring this over to the other side, minus m2 v2 prime, which equals to m1 v1 prime. Okay, divide out the m1s. So I'm going to have m1 v1 divided by m1 minus m2 v2 prime divided by m1, which equals to v1 prime. So I'm solving for v1 prime. I'm solving for one of the equations. Okay, so one of the unknown variables. So m1 and m1 cancel out. You're left with v1 prime, which equals to v1 minus m2 over m1 times v2 prime. Okay. All right. So now what we're going to do is we're going to sub our numbers in. And this is what's going to come out to v1 prime, which equals to v1, which was 1.3 meters per second, minus, this is 1.3 right there, minus m2, which is 0.15 kilograms, divided by 0.26 kg, which equals to, oh, we already did that, times v1 prime times v2 prime. Times v2 prime. Okay, can somebody divide those two for me, please? 0.15, how much is it? 0. So don't round it, please. Another thing that you do is do not round it. So 1.3 minus 0.72. Can you do that again? Yes? Huh? 5, 7. Oh, how'd you get 7 to? You couldn't have done the whole thing because you can't solve it yet. So 0.577 V2 prime. Now remember, this is an unknown. We don't have V2 prime. We do not have V2 prime. Okay. All right. So what we're going to do next is, bear with me. I'm going to erase some of this part, some of the stuff at the top, and we're going to continue the question. So now what we need to do is we need to take a look at our energy, kinetic energy before and after the collision. Okay. So my kinetic energy was half m1 v1 squared plus half m2 v2 squared, which equals to half m1 v1 prime squared plus half m2 v2 prime squared. Okay? Energy of both of the objects before the collision, energy of both the objects after the collision. Now I'm going to multiply this by 2 to get rid of the halves, and I get m1 v1 squared plus m2 v2 squared, which equals to m1 v1 prime squared plus m2 v2 prime squared. Okay, now of course this is 0 because this times 2. I'll multiply it by 2. Okay, so this one right here is 0.26, okay, times 1.3 squared, which equals to 0.26 times v1 v1 prime squared plus 0.15 times v2 prime squared. Okay. Okay, can somebody do that for me right here? So what do you get? 0. Don't round it up. It's not 44. That's correct. Thank you very much. 0.4394. So my suggestion is at least have 3 to 4 decimal places. Do not round it up, because otherwise your final answer might be slightly incorrect. I mean, it might be slightly off. Okay. So what we're gonna do next is we're gonna do 0.26, and we're gonna sub in this v1 prime into here. Okay, we're gonna sub in this v1 prime into here. So you end up with the following equation. It becomes to look like this. It's going to become v1 minus m2 over, well, we already have the answers for there, so let's just plug that in. It's going to be 1.3 minus 0.577 v2 prime, and then we're going to square it. v2 prime squared plus 0.15 v2 prime squared. I know there is so much happening. There's a prime, there's a 2, and there's a square, and yeah, they all look the same. So the potential for making mistakes, simple mistakes, is very, very high. So my suggestion to you, don't jump steps. I know you guys are all super smart. Show me all the steps if you want to get the marks. Okay? Because I know there are so many places that you're going to make mistakes. Yes? Same, still five TI questions. But, you know, just like projectile motion, you remember projectile motion took so long in the beginning, but by the end of the chapter, you were able to get through it really, really quickly. So the more you practice these questions, the better you will get at them.